Hey everyone, in this last video for chapter 4, what we're going to do is talk some about the physical properties of these types of stereoisomers that we've been talking about. We're going to then talk about a method, an instrumental method, that we could determine the difference between enantiomers. So let's look first at the physical properties of enantiomers. Okay. In an achiral environment, like a normal solvent or in the air, they are going to have the same melting point or boiling point. They've got the same polarity, the same solubility, the same reactivity. So in general, we cannot tell one enantiomer from another. All right? The differences that they have are that they can react differently if they're in a chiral environment. All right, so they have the same reactivity in an achiral environment, but they'll have they can have different reactivities in chiral environments. And so an example of that might be a drug molecule that's chiral will react differently than its enantiomer if it binds to a protein, because proteins are chiral molecules as well. So the way that we can tell the difference between those is to essentially use a method which interacts differently with different enantiomers. And so the approach that we're going to use is to look at the interaction of the chiral molecules with what's called plane polarized light. Okay, so before I go in and talk about those, let's think a little bit here about diastereomers. Okay, how are they going to have similarities and differences? All right, so diastereomers, they're still isomers, right? So they're very similar to one another, but they're not mirror images. So in general, diastereomers are just treated as different molecules. They'll tend to have different melting points and boiling points. They'll have different polarities, solubilities, reactivities. You know, they may be very similar, but they're going to be different from one another. So in general, diastereomers are just different molecules with different properties. All right, so let's look at this method of using plane polarized light. All right, so here's a diagram of what the type of instrument might look like that we would use. This is instrument is called a polarimeter. All right, and so it uses some light source, and light in general, remember, light is made up of waves like this, and when we have it coming from a light source like a light bulb, those waves can be oriented in any different direction. Okay, so each of these lines could be a wave, but they're oriented in all these different directions. Okay, so we run this normal light through what's called a polarizer. And a polarizer you can think of as just having a slit down like this. And so only the light that has its plane that's lined up with the slit will pass through. And so we get only a single plane of light. All right? So if you take two of these polarizers and turn them 90 degrees, then no light will pass through. And in fact, this is what happens if you have some polarized sunglasses. And if you have two pairs of polarized sunglasses, if you turn one lens 90 degrees to the other, almost no light will pass through at all. All right? So this plane polarized light, though, can interact differently with chiral molecules. All right, so here's a first diagram of what would happen if this plane polarized light reacts with an achiral molecule. All right, so we got the same thing. We got the light source, normal light coming out, gets polarized, so we have a plane polarized light. So it's going to pass through some kind of container that holds our sample, usually a solution of our sample. If this molecule, if the molecules in the sample is achiral, then essentially the plane of the light passes through unchanged. So nothing happens, it just stays in line. If we pass this light through a solution of a chiral molecule, the plane of the light gets rotated. Okay, so it rotates either clockwise or counterclockwise from where it started. If it rotates clockwise, we call it dextrorotatory. Dextrorotatory. And we tend to give it a plus sign, so this is a positive rotation. If the light is rotated in the counterclockwise direction, it's called levorotatory, or minus. All right, so we can rotate right, clockwise, or counterclockwise. So in the last slide, we said that if it passes through a solution of an achiral molecule, then it passes through unchanged. Now, can you think of another situation where it would pass through unchanged? All right, we could have it pass through unchanged if it has an equal mixture of enantiomers, because one enantiomer will rotate the light in one direction, the other enantiomer will rotate it in the other direction, so it essentially cancels it out. All right, and so a one-to-one mixture of enantiomers is called a racemic mixture. So a one-to-one mixture of enantiomers is called a racemic mixture. Okay, and a racemic mixture will not rotate the light. All right, now the amount of rotation depends on a number of things. One is it depends upon the concentration of that molecule in solution. So essentially, the more molecules that are in solution, the more the light will be rotated. The next one is that it depends on the sample container. Essentially, depends on the length of the sample container, right? So this is usually in decimeters. So 1 decimeter. So it's 10 centimeters. Okay? Depends on the temperature, and it also depends upon the wavelength of the light. Because we would like to be able to compare the results of an experiment with a polarimeter, so we could measure what we call the optical rotation from different places and with different concentrations, what we do is we usually report a different value, which is called the specific rotation. And so this is usually just normalized for the concentration, right? So because the higher the concentration, the stronger the rotation. If we essentially divide by the concentration, we get a value called the specific rotation. And here's the equation for this down here. So this alpha value, this is our measured rotation, or our observed rotation. This is what we would get from the instrument. Okay? The L is the length of our sample container. Okay, And like I said, this is usually in decimeters. All right? And C is the concentration in grams per milliliter. All right, so the other parts of this is that T over here is the temperature. Okay, so we don't really have an equation that that will calculate the effects of temperature. However, what we usually do is we report the temperature at which the measurement was made, so if somebody really wanted to repeat that, they could. And lambda is the wavelength of the light. Okay, typically we often use what's called the sodium D line, okay, which is at 589 nanometers. So sometimes we just put a D there instead of a lambda if it's the what we call the alpha D, or the specific rotation. All right, so this allows a person to measure a specific rotation in one place and always compare the value that somebody got somewhere else. Okay? So molecules that are chiral that rotate the plane of polarized light are called optically active. Are optically active. Okay? So an achiral molecule will be optically inactive. A racemic mixture of chiral molecules, so an even one-to-one mixture of enantiomers, will also be optically inactive. All right, so one other thing is that the direction of the rotation that we observe doesn't depend directly of whether the chiral center is RS. It depends more on the molecule in total. All right, so here's a couple of examples. Here's lactic acid, right, that builds up in your muscles when you work out. So here we have two molecules. We've got lactic acid and then sodium lactate. So that's the sodium salt of the carboxylic acid. All right. Notice that in this case, all that's been done is convert the acid into its conjugate base, and the optical rotation goes from being dextrorotatory to levorotatory, even though the chirality S remains the same. So a given molecule with an R chiral center could have a plus or a minus rotation. Molecule with an S chiral center could have a plus or minus rotation as well. However, if we take the same molecule and we look at its enantiomer, it will have exactly the opposite specific rotation. Okay, so the enantiomer will rotate the opposite in the light in the opposite direction and to an equal amount. So here's an example. If we had R 2-methyl-1-butanol versus S 2-methyl-1-butanol, so these two are mirror images. They are enantiomers, and if we keep the light the same, the temperature's the same, notice that the R compound has a specific rotation of plus 5.75. The S enantiomer has a specific rotation of minus 5.75. So these specific rotations can go anywhere from, a small number up to, a couple hundred. All right, so they can have quite a large range. Okay, so the last thing we're going to look here is how we might measure the purity of enantiomers. So sometimes we have a pure enantiomer, sometimes we may have a mixture of enantiomers, which is 70-30 or 60-40, right? It might not be enantiomerically pure. And so when we have it enantiomerically impure sample, we can measure or we describe it in terms of an enantiomeric excess. What this really is what percentage we have of one enantiomer, or it's really the amount of one enantiomer that we have in excess of the other enantiomer. So the way that we measure this is we just divide the observed specific rotation of the solution. So we'd have to measure the rotation and calculate, divide by this cell, the sample container length, and divide by the concentration to get the specific rotation. And we divide that by the specific rotation of the pure enantiomer. So how much rotation we would get if we had a pure enantiomer. And then we multiply that by 100. So an example here is that if we had a pure enantiomer that gave a specific rotation of 23.1, and we had a mixture that gave us a specific rotation of 9.2, we divide these times 100, and this would be called 40% enantiomeric excess. All right. A 40% enantiomeric excess would result from a 70-30 mixture of enantiomers. Okay, because what we're just observing is what's in excess. So if we have 30% here to the 30% over here, this part would be essentially racemic. So they would cancel each other out, and we are left with 40% excess. All right? So that's how we would deal with this. So in biological systems, molecules are almost always made as as a single enantiomer. So in biological cycles, sugars in the body, proteins, all these kind of things, these are enantiomerically pure compounds. There are ways to synthesize enantiomerically pure or almost enantiomerically pure compounds in the lab, but sometimes we get some mixture. So you might get this 40% or 80% enantiomeric excess, and so we need to be able to know how to analyze those. Alright, so in this chapter we talked about some different types of stereoisomers. We reviewed some of those. We learned a new type of stereoisomers that involves chirality. And we learned that we can have chiral molecules if we have chiral centers or asymmetric centers. We learned how to distinguish between different chiralities, and we learned this R and S nomenclature in order to do that. We learned that if we have more than one chiral center, we have some new kinds of stereoisomers as well. So diastereomers are stereoisomers that are not mirror images. And then we have kind of a special circumstance where we have more than one chiral center, but the molecule has a plane of symmetry, making it achiral. That's called meso. All right, and the last thing we looked at is about the physical properties of enantiomers and diastereomers. We talked about how we could use a technique called polarimetry, which uses plain polarized light to analyze enantiomers and the ratio of enantiomers.